In this video, I will show you 3 simple circuits to power ESP32, Arduino or any project from 12 volt DC to 240 volt wall power. It's really no rocket science. I will walk you through the datasheets to show you how to build your own mini power supply. Then I will test each circuit to show the operation in real life and compare all 3 based on performance and price. Let's start with a short introduction of the 3 circuits. The first circuit is based on the LM2576 adjustable, 40 volts 3 amps output. It is a powerhouse classic, adjustable, fully protected, rugged and perfect for high power builds. The second circuit uses its small brother, the LM2594, 5 volt. The tiny SO8 package makes it ideal for a compact project. The third circuit uses the MP172, which has a 700 volt built-in switch. It can handle 240 volt AC in an SOT23-5 package. It delivers 120 milliamps, but if you need more current, you can use the MP175, which can do 600 milliamps. Now let's go to the first circuit. The first circuit is the LM2576. It is famous because it is used in the cheap 3 amp DC-DC modules you can buy online. It's an old IC from the TI Simple Switcher family, and it is simple indeed, only 7 components, so you do not even need a PCB to try it. It is a buck converter with an integrated MOSFET power switch between V-in and V-out. Here I use the adjustable version, but there are also fixed output versions for 3.3, 5 and 12 volt. Let me open the datasheet to explain how to select the components. Let's start with the input and output capacitor. On page 15 of the application note, it is recommended to use a 100 microfarad electrolytic capacitor at the input. Make sure the voltage rating is enough. 63 volts will be okay for 40 volts. For the output cap, we go to page 16. It is recommended to use 220 to 1000 microfarad. I use 1000 microfarad to make sure the ripple is not too high. As the output voltage is only 5 volts, the 16 volt capacitor for sure will be enough. Then the catch diode. For the diode, you need to use a fast recovery or a Schottky diode with a 3 amp rating. Also here, make sure the voltage rating is enough. The diode must be able to withstand the input voltage. Table 8.3 shows some examples of suitable diodes. I use a 1N5822. It is a 3 amp 40 volt Schottky diode and it was quite easy to find. So now we have selected the input capacitor, the output capacitor and the diode. Now let's have a look at the feedback resistors. This adjustable version of the IC will try to reach 1.23 volt at the feedback pin. So the output voltage can be calculated with this formula. In our case we will get 4.92 volt on the output, close enough to 5 volts. I have used very low resistor values of 120 ohm and 360 ohms. This to ensure a strong reference signal. You can also use higher values like 1.2K and 3.6K, but avoid going too high as this will weaken the reference signal and make it more sensitive to noise. Now let's select the inductor value. Because the LM2576 buck control IC supports 2 operation modes, continuous and discontinuous mode, you are very flexible in the inductor selection. Let me explain shortly. When the integrated MOSFET is on, the current in the choke will increase. When the MOSFET is off, the diode takes over and the current in the choke will decrease. And the energy is released in the output capacitor. The control concept is very simple. The frequency is fixed. The IC only controls the on time to charge the inductor with energy. If the output voltage is low, the feedback pin will sense this and the IC will increase the on time, so more energy will flow into the capacitor. If the output voltage is too high, the IC will decrease the on time and less energy will flow into the output capacitor, so the voltage will drop. In this case, we have a light load, so the on time is short, and when the diode takes over, the current will eventually reach zero. Then we start again. This is called DCM, or discontinuous conduction mode. Now if we increase the load, the on time will increase and you will reach a point where the current will just reach zero. That is still okay. Now if the load further increases, the current will not reach zero anymore, like here. That is not a problem. On the contrary, this is called CCM, or constant conduction mode. The inductor current will never reach zero, but the IC still controls the on time. So if the output voltage is too high, it will just reduce the on time, so the energy to the capacitor will decrease and the output voltage will drop. If the load becomes even lower, we go back to discontinuous mode. If you use a small inductor, the current will rise very quickly. If you use a big inductor, the current will rise slowly. So with a small inductor, it will be more likely to be in discontinuous mode. With a big inductor, it's more likely to be in continuous mode. In both cases, we get 5 volt on the output, so no problem. Now there is of course an optimum choice for the choke, but to make it work, it's not too critical. I suggest to follow the example in the datasheet. For this one, 100 microhenry works well. A drum choke should look like this, and it should be about 1 centimeter high for this application. To measure the value, I use a cheap component tester like this. Enough talking now, let's build and test it. So here's the circuit running at 30 volts in, 5 volts out. No load, and on the oscilloscope here you see the voltage on pin 2 of the IC. The 3 multimeters measure the IC temperature, the output current and the output voltage. Let me explain the waveform. The circuit is in DCM, or discontinuous mode. Here the MOSFET is on, so the voltage on point 2 is high, 30 volts. Here the MOSFET is off. The voltage drops to zero until it wants to go negative, and then the diode takes over the current and pushes its energy into the output capacitor. Here both the MOSFET and diode are off, so pin 2 of the IC is floating. Some residual current in the parasitic capacitances and the inductor causes this ringing. Now I increase the load. More power is consumed, so the IC will detect the output voltage wants to drop and decreases the on time. Now the inductor will absorb more energy each period, so we maintain the output voltage at 5 volts. If I further increase the load, you see that the ringing is gone. We are now entering continuous mode. The current in the choke is never zero anymore. Good for the choke, but not for the diode. Now the MOSFET will switch on while the diode is conducting. This forces the diode off every cycle. I use a Schottky diode, which is super fast, so it can easily handle this. This is why you need to use a fast diode. A general purpose slow diode like a 1N4001 cannot handle this. Let me further increase the load to 1 ampere. The temperature of the IC is slowly increasing. Let's keep it running for a few minutes to get a stable temperature. Now the thermal protection has become active. So the LM2576 circuit worked well up to 500 milliamps. But at 1 amp something went wrong. What happened? Well, actually my cheap component tester already showed the problem, but I did not pay attention to it. Here you see I removed the sleeve. To save costs, the inductor uses very flimsy copper wire. I tried it with 1 ampere DC, it already heated up to 72 degrees. In the circuit it will have peak currents of 1.5 amps. Adding high frequency and magnetic losses, well, you get the point. When the inductor overheats, the core will lose its magnetic properties, so the circuit cannot work properly. This does show that the LM2576 IC is very robust. Its protections did prevent the circuit to fail. I repeated the thermal test and wrapped the inductor with some thermal pads to control the temperature at higher currents. The IC reaches 70 degrees at 1 ampere, which is pretty good for my flying wire construction. Normally you place the IC on a PCB and add a copper area to the tab to absorb the heat. By the way, if you want to make a PCB layout, there is a reference layout in the specification. You can roughly follow the part placements and the tracks. Let's look at the availability and cost. The LM2576 is a popular IC. It's quite easy to buy online. It will cost a bit more than €2. The Onsemi one is the cheapest I could find. By the way, there's also a leaded version, so you can solder it on a prototyping board. Now let's go to the next circuit. The LM2594 is like a smaller version of the LM2576, also from the TI Simple Switcher family. The IC comes in a tiny SO8 package and can deliver 600 milliamps of current. The schematic here shows the fixed output 5V version, which only needs 5 components. Let me open the datasheet to show you how to select the components. Let's start with the input capacitor. On page 12, it is recommended to use 68 microfarad for the input capacitor. Make sure that the voltage rating is enough. A bigger capacitor will not affect the performance of the IC. For the output capacitor, we go to page 11. It is recommended not to use capacitors larger than 220 microfarad. I actually used 1000 microfarad and it worked, but I suggest that you do use 220 microfarad. I suspect that a very large output capacitor takes too long to charge at startup and may trigger the short circuit protection of the IC. But it's not explained in the datasheet. Then let's select the diode. For the diode you need to use a fast recovery or a Schottky with at least 1 ampere current rating. And of course a high enough voltage. Table 8 shows recommendations for diodes. A 1N5819 should be quite easy to find. Now let's select the inductor. On page 16, figure 22, the graph shows that 220 microhenry is the most optimal for 100 to 300 milliamps. I use 220 microhenry. Now let's power it up and test it. Here's the circuit running at 30 volts in, 5 volt out. On the oscilloscope you see the voltage on pin 8 of the IC. The 3 multimeters measure the IC temperature, the output current and the output voltage, which is now 4.95 volts. The circuit is running in discontinuous mode. Here you see the ringing, just like we saw with the other IC. Now let me increase the load current. More power is consumed, so the IC will detect the output voltage wants to drop and increases the on time. At about 70 milliamps, we just entered CCM or continuous conduction mode. Note that the switching frequency is 160 kHz. That's about 3 times higher than with the previous IC. Let me further increase the load current. We are now at about 300 milliamps and the IC maintained the output voltage to 5 volts. Let me now increase the load current to 600 milliamps, which is the limit of this IC. Okay, more than 600 milliamps, so that works very well. Let me now do some thermal tests at different currents. I measured the temperature of the IC over the load range. The IC reaches 72 degrees at 600 milliamps, and that with my flying wire construction. Normally you place the IC on a PCB and add a copper area to the tap to absorb the heat. If you want to make a PCB layout, you can find a very good reference layout on page 30 of the datasheet. So with the LM2594 circuit, you only need 5 components to build a power supply that can deliver 600 milliamps at 5 volts. Let's now have a look at the availability and the cost. The LM2594 is a popular IC and also quite easy to buy online. I found the adjustable version from onsemi for about €2. Both the LM2576 and the LM2594 can support voltages up to 40 volts. The HV versions up to 60 volts. The next circuit I will show you is suitable for high voltage and can power your project directly from the mains. Let's have a look. This is the MP172, which has a built-in 700 volt switch. This way it can handle 240 volt AC in a very tiny SOT23 package. It delivers 120 milliamps, but if you need more current, the MP175 can do 600 milliamps. The circuit is a bit more complicated. 11 components. Let me explain. Here you connect the mains, and this diode is a peak rectifier. So on this E-cap we have about 320 to 340 volts DC. The MP172 has a MOSFET switch from pin 5 to pin 3. So here you see the buck inductor, the buck diode and the output capacitor. The feedback circuit looks like the LM2576, but it needs some more components. This 2.2 microfarad capacitor is a bootstrap capacitor. It is charged by the IC and acts like a portable power supply for the circuit part in the IC that goes up and down with the source. Then this diode and the 100 nanofarad capacitor are used to sample the output voltage. When this diode is conducting, the voltage on the source is low. So the 100 nanofarad capacitor will be charged to Vout. So with this capacitor we sample the voltage of the output. The feedback pin can detect the voltage via the 2 resistors. If the feedback pin detects less than 2.55 volts, the IC will control the switching timing to increase the output. If it's more than 2.55 volts, the IC will decrease the output. So the output voltage can be calculated with this formula. In this case, R1 is the same as R2, so the output voltage will be 5.1 volts. Let me open the datasheet to explain how to select the components. Let's start with the input capacitor. It is not critical for the operation. A few microfarad will be enough. What is important is protection against surge, as mentioned on page 14. Surges are voltage spikes on the mains caused by switching of electric motors or large loads like heaters. Your MP172 can only handle 700 volts. You can protect it with some impedance and a larger input capacitor. So except for the diode here, you need to add some resistance, and I suggest you also add a fuse. The resistor should be a fused resistor of about 20 to 50 ohms. For the inductor selection, I just followed the reference design on page 16 and used 1 millihenry. The current is limited, so a normal drum choke will work fine here. For the buck diode, I recommend an ultra-fast 25 to 45 nanosecond 600 volt 1 amp diode. Ultra-fast is the best for efficiency in continuous conduction mode. I use an HS1J, which is a 600 volt 1 amp 75 nanosecond diode, and it works fine. For the sampling capacitor, I use 100 nanofarad. That's more than the 22 nanofarad in the reference design on page 16, but I also use lower sampling resistor values. Before we power up the circuit, I want to give you some warning about the dangers of high voltage. The next circuit uses mains voltage, 120 to 130 volts, which is lethal It can shock, burn, or kill you, or your family members. Never leave it unattended. Wear safety glasses. An isolation transformer helps, but it's still not safe unless you exactly know what you're doing. This is not for beginners. If you're unsure, do not build this. You are fully responsible for your safety and others around you. Here's a circuit running at 30 volt AC in, 5 volt out. I will increase the voltage to 230 volt in a moment. On the oscilloscope, you see the voltage on pin 3 of the IC. The 4 multimeters measure the IC temperature, the output current, the AC input voltage and the DC output voltage. The circuit is running in discontinuous mode. Here you see the ringing, the same as we saw with the other ICs. Let me change the time base. If I increase the load current, you see that both the frequency and the on time change. Now for safety, I will disconnect my PC oscilloscope and increase the input voltage to 230 volt. Okay, disconnected. Now I increase the input voltage. That is about 230 volt. I use an isolation transformer and do not touch the circuit. The load current now is 28 milliamps. Let me increase it. That's about 60 milliamps. The IC temperature is about 30 degrees. Let me further increase the load current to 120 milliamps, which is the limit of this tiny IC. 123 milliamps. The output voltage is still about 5 volts, and the temperature of the IC is slowly increasing. So that worked very well. I did some thermal tests at different currents for the MP172 circuit. The datasheet mentioned the maximum output current is 120 milliamps. But there's some margin though. I tested up to 158 milliamps and the temperature reached 56 degrees. If you need more current, you can check the MP173, 74 or 75. The last one goes up to 600 milliamps. Let's have a look at the availability and the price. The MP172 is not as common as the LM25XX series from TI, but with about 3000 pieces in stock, it's still quite easy to buy online. I found it for 1.7 euros. The 600 milliamp MP175 will cost you 1.8 euros. Now let's conclude and compare the three circuits. Here's an overview of the results of the three circuits. With the LM2576, our powerhouse classic, it is very easy to build a powerful low voltage power supply. And up to 500 milliamps, the component choice is not very critical. This here is the adjustable version. If you take the fixed 3.3, 5 or 12 volt version, the circuit is even more simple. The LM2594 is more compact, but for the rest quite comparable to the LM2576. Even the price is almost the same. Then the MP172. Super compact, and it can power your project directly from the mains. However, 120 milliamps is not much, and ESP32 will need about 300 milliamps. So I will try the MP175, which only costs 10 cents more. In the datasheet, it's mentioned not to use it below 70 volt DC, but it seems to work fine at 24 volts. All ICs are very robust and have many protections, like overload or over temperature. They are not as critical to component values as I expected. Now let's have a look at the thermal comparison. Here you see the thermal comparison of the three ICs. The LM2576 is clearly the most powerful. Make sure you check the inductor temperature and don't overheat it like I did. The LM2594 is suitable for most projects, including the ESP32. It can deliver up to 600 milliamps. The MP172 can only deliver 120 milliamps, enough for one Arduino, but for many projects you may need more. So if you want to power your project from the mains, you will probably need an MP174 or 175. Now for some general tips. First, check how much power you need. Measure the current consumption of your project. Then every datasheet has an example or a reference design. I recommend you to start from that. Take your time to read the datasheet and try your circuit on a higher load than a normal application. And the last tip, safety first. Mains voltage is lethal. I hope you liked the video. If it was useful for you, please like and subscribe. And write your experience in the comments.